So today we will learn uniqueness of the solution of first order ordinary differential equation. In a previous video, we showed how to obtain the solution of first order ODE using integrating factors, and we have explicitly written down the solution for the first order ODE. Today we will discuss the uniqueness of the solution of the first order ordinary differential equations. For example, of the Newton's law of cooling, the rate of change in temperature is proportional to the difference between the object's temperature and the ambient temperature. And we can write a integrating factor e to the power kt and multiply the differential equation with e to the power kt and write the left hand side as a total derivative. Temperature as a function of time is equal to T ambient plus this difference multiplied by e to the power minus kt. So when T goes to infinity, this term becomes negligible, the second term, and the temperature at T equal to infinity is equal to the ambient temperature. This is a prediction from physics that at T equal to infinity, the temperature of the body will be equal to the ambient temperature. But this prediction needs an underlying assumption, which is that the solution is unique. Unless the solution is a unique solution, then the prediction will not be very sound because there will be many solutions. So it is important to prove the uniqueness of the solution. We can give another example, that is the RC circuit. In a RC circuit, the potential across the capacitor satisfies a differential equation. This is first order differential equation. And again, we can write down this integrating factor e to the power t by RC, multiply this equation with the integrating factor, and then write down the solution. The solution is here. And when t goes to infinity, and then this term obviously is negligible, the second term. Just for the sake of understanding, we can take an example where there's a constant input voltage. Then this constant will go out of the integration, and this integration will give e to the power t by RC multiplied by RC. And this RC will get cancelled. E to the power minus t by RC and e to the power t by RC will give 1, and so we will get V0. That means the voltage across the capacitor will be equal to V0, which is the inhomogeneity here, V0 in the right hand side. That is the external voltage. So the capacitor voltage will be equal to the supply voltage. So again we see that we need the proof of uniqueness for this kind of differential equations. So with this motivation in our mind, we will try to prove mathematically the uniqueness of solution. This is a typical first order differential equation. This is the inhomogeneity term, Qx on the right hand side. So suppose there are two solutions, y1 and y2. And then we will prove that y1 minus y2 equal to 0 for all x. So that will prove that the solution is unique. So for that, let us define ux equal to y1x minus y2x. And then try to prove that u as a function of x is 0 for all values of x. So how do we prove? So if there are two solutions, both will satisfy the differential equation. So first one is here y1 prime x px y1 x qx This is the first solution. We substitute the first solution. Then again we can substitute the second solution because both are solutions. So we get two equations. And then if we subtract 3 from 2, then we get from here y1 prime x minus y2 prime x. And here we get px multiplied by y1 minus y2. Here we get 0. So then we get u prime x plus px ux equal to 0. So that means the difference, that is the ux, it satisfies the homogeneous equation. So we started with a differential equation and the difference satisfies the homogeneous part of this differential equation. Now let us define a new function, Vx, e to the power integral px dx ux, and take the derivative of Vx with respect to x. Then we get two terms, derivative of this ux plus this into u prime x. So if we take e to the power integral px dx as common, we get within bracket u prime x plus px ux. But this is the homogeneous part, the original differential equation, and we have already proved that this is 0. That means v dash x equal to 0. If v dash x equal to 0, that means if the derivative is 0, that means vx equal to constant. Let us find out what is. So for that, let us put the initial conditions. Suppose the initial condition is ya equal to b. Then both of them are solutions, that is y1a equal to b and y2a is also equal to b. That means u at the point a is y1 at the point a minus y2 at the point a, which is b minus b, because this is b, this is 0. That means u at the point a is 0, but the solution is vx equal to constant. So we can find out this constant using what we have got, ua equal to 0, because va equal to e to the power integral px dx multiplied by ua. So v at the point a is e to the power integral px dx multiplied by u of a, and u of a is 0. So that means we get v of a is 0. If v of a is 0, that means the constant is 0 because v of x is constant, because vx is e to the power integration px dx ux, and this is equal to 0. But this part cannot be 0, so ux is 0, because vx is a product, because vx is the product of e to the power integral px dx into ux, and e to the power integral px dx cannot vanish, so ux must vanish. So ux equal to 0 for all values of x. That is, ux equal to 0 for all values of x means y1 of x is equal to y2 of x for all values of x. Therefore, we get the original differential equation must have a unique solution. So I hope this was interesting, and thank you for watching.